All right, welcome. Today, we're going to pull back the curtain on something that makes your computer actually feel fast and responsive. We're talking about the invisible workforce inside every single one of your apps, computer threads. So, let's dive right in and figure out how this unseen team gets the job done.
You know the feeling. We have all been there. You click a button, and suddenly, nothing. You get the rainbow wheel of death, the little hourglass, or that dreaded not responding message. It is one of the most maddening things in modern computing, right? But what's really going on under the hood?
Well, a lot of the time, the culprit is a single worker. Imagine your application is a big project, but you've only assigned one person to do all the work. If that lone worker gets bogged down with a really tough task, say downloading a massive file, the entire project just grinds to a halt. Seriously, nothing else can happen. The app can't even update the screen to show your mouse moving until that one job is finally finished.
So, if having a single worker is the problem, what's the solution? Well, you assemble a team. And in the world of computing, these team members are called threads. They're basically these lightweight workers that all operate inside a single application.
Okay, to really get this, let's nail down the key difference here. A process, that's the entire project. Think of it as the office building, the budget, the whole shebang. It's a heavyweight program with its own dedicated resources. A thread, on the other hand, is like a team member within that project. It's just a lightweight path of execution that shares all the project's resources, the office, the tools, with everybody else on the team.
So why is this team approach so much better? Well, first off, you get responsiveness. If one worker gets stuck on a hard task, the rest of the team keeps things moving. The app doesn't freeze. Then there's resource sharing. The whole team uses the same office and tools, which is just way more efficient. It's also about economy. Hiring a new team member, creating a thread, is so much cheaper and faster than starting a whole new project. And finally, you get scalability. A bigger team can handle way more work, and you can take full advantage of modern multi-core processors by giving different tasks to different workers at the same time.
Okay, so we have our team, but how do they actually get the work done? Well, it kind of depends on the hardware they have to work with. And there's a really crucial difference between looking like you're doing many things at once and actually doing many things at once.
First up is concurrency. Imagine one super skilled worker, that's your single processor core, who's an expert juggler. They work on task A for a millisecond, then they switch to task B, then to C, then back to A. It's all happening so blindingly fast that to us, it looks like all the tasks are happening at the very same time. It's this brilliant juggling act that makes even a single-core CPU feel responsive.
And this is parallelism. This is no illusion. This is the real deal. This is having multiple workers at multiple workstations, multiple processor cores, all doing their jobs at the exact same moment. You've got one core updating the display, while another one is fetching data from the whip. This is true simultaneous execution, and it's the superpower of all our modern multi-core systems.
So, you've got this team of threads ready to go, either juggling tasks or working in parallel. But who's in charge? Who decides which thread gets to run, on which core, and for how long? Well, that's where the operating system's kernel comes in. You can think of it as the ultimate project manager.
Think of it like this. Your application assembles the user threads. That's our team of workers. But for any of them to actually do real work on the CPU, they need a manager's approval. Those managers are the kernel threads, and they're controlled directly by the operating system. The way these workers and managers relate to each other, well, that defines the management style.
Let's start with the first and, honestly, the simplest model, many to one. It's pretty much what it sounds like. You can have a whole bunch of team members, but they all have to report to a single manager.
Now, the huge problem here is the bottleneck. Since every worker reports to that one manager, if just one of them has to wait for something, that single manager gets completely tied up. And since everyone else needs that manager's approval to work, the entire team is put on hold. This model also makes it impossible to get any true parallelism on a multi-core system.
Next up, we have the one-to-one model. This is the approach used by most modern operating systems like Windows and Linux, and it's a massive step up.
In this style, every single team member, every user thread, gets its own dedicated manager, its own kernel thread. This is fantastic for parallelism. If one thread gets blocked, it doesn't affect anyone else. The only downside? It creates a bit more overhead. Having a dedicated kernel thread for every user thread can use up resources, so operating systems will often limit the total number of threads an app can create.
So that brings us to a really flexible hybrid approach that tries to get the best of both worlds, the many-to-many model.
Here, the operating system creates a flexible pool of kernel thread managers. Then, the workers, our user threads, are dynamically assigned to any manager that's available. This means you can have a really large team without needing a personal manager for every single member. It gives you that awesome parallelism of the one-to-one model, but without all the overhead. It's a really smart, efficient compromise. Okay, so let's just quickly recap these management models. Many-to-one is simple, but forget about parallel work, and there's a huge risk of the whole app blocking. One-to-one is great for parallelism, but it has higher overhead. And many-to-many gives you the best of both, parallelism with a lot more flexibility. You can see the clear trade-offs system designers are constantly weighing between simplicity, power, and efficiency. All right, enough of the theory. Let's talk about where you actually see this unseen workforce in action every single day. And the answer is, well, it's everywhere. Just think about your web browser for a second. There's one thread that's busy updating the display and responding to your clicks. At the same time, another thread is working in the background, fetching all the data and images from the internet. Or in your word processor, one thread is handling your typing while another one is doing that real-time spell check. On a big web server, you could have hundreds of threads all working in parallel, each one answering a request from a different user across the globe.
And the scale of these digital teams can get absolutely staggering. Take a modern server CPU like the Oracle Spark T4. It has 8 cores, but get this. Each of those cores can handle 8 hardware threads. So you do the math. That's a single chip executing 64 different tasks in true parallelism, all at the exact same instant. It's wild.
So here's the crucial point, the main takeaway. The next time your application feels magically fast and responsive, like it's doing a million things at once without even breaking a sweat, you can thank this unseen team. Threads are the fundamental building block that makes the fluid, powerful, multitasking software experience we all just take for granted possible.
And that leaves us with a pretty fascinating question for the future, doesn't it? As we start moving from tens of cores to hundreds, maybe even thousands on a single chip, how are we going to manage these massive, ever-growing digital teams? Figuring that out is really the next frontier in computing. Thanks for joining this explainer.